Welcome to lesson 4.5, Prove Triangles Congruent by ASA and AAS. So let's begin with our postulate and theorem that makes sense of our title. We've already looked at some of our other congruence postulates and theorems. Now we're adding two new ones in this lesson. The first one is postulate 21, which makes up the ASA part of the title. That is the angle-side-angle congruence postulate that states if two angles and the included side of one triangle are congruent to two angles and the included side of a second triangle, then the two triangles are congruent. So what they mean by an included side, we looked at an included angle in our last lesson, which was where the two sides meet. The included side is the side that is in between the two angles. So if I'm looking at angle A and B, the included side is side AB. If I'm looking at angles D and E, the included side would be side DE. And then we have theorem 4.6, the angle-side congruence theorem. And that theorem states if two angles and the non-included side of one triangle are congruent to two angles and the corresponding non-congruent side or corresponding non-included side of a second triangle, then the two triangles are congruent. So if in these two triangles we knew angle A was congruent to D and B was congruent to E, then we could use side AC or side BC. Those are our two non-included sides, and then DF or EF. So in this case, we have angles A and B and side BC. So the corresponding side to BC would be side EF. So that would go angle, angle, side. The one above it, angle, side, angle. So example 1. Can the triangles be proven congruent with the information given in the diagram? If so, state the postulate or theorem we would use. So in diagram A, they told us this angle here in the upper left is congruent to this one in the bottom right. Then the upper right here is congruent to the bottom left there. And these two here are vertical angles, so they're congruent to each other. But we do not have a postulate or theorem that is angle, angle, angle. So without knowing any side lengths, we could not say these two triangles are congruent. In B, we have this angle out here congruent to this angle here, the two angles near the top congruent to each other. So we have two angles, and then these triangles share this side. So that side is congruent to itself. So in this case, we have angle, angle, side, angle, angle, corresponding side. So yes, these two triangles are congruent by angle, angle, side. And then in C, again, we're going back to this idea that vertical angles are always congruent. So the vertical angle created here in the middle tells me this angle here congruent to this angle here, shown by the blue arcs. So now, on the upper triangle, I have an angle, a side, and an angle. On the bottom triangle, I have an angle, included side, and an angle. So that one would be congruent by angle, side, angle. So don't forget, if they share a side, that side's congruent to itself. If they have vertical angles, those angles are always congruent. Now if we look at D and E, so in D, we're trying to say, is SUT congruent to UVW or VUW? So what we know again is we know they share a vertical angle here at U, S and V are equal, which tells me down here this angle would equal this angle. But again, I only know 3 angles. These triangles do not share a side, so I cannot say for certain that these are going to be congruent triangles. And then in E, we have a 90-degree angle up here for STW, and then a 90-degree here for TWV. So each triangle is a 90. Each triangle then has an angle congruent to each other, and they share this side. So we have an angle, a side in the middle, and the angle. Angle, side in the middle, and the angle. So yes, they're congruent by angle, side, angle. Now, if we were going to write the congruence statement for this triangle, S matches up with V, and then T with W on the other one. So if we name this triangle STW, then we would have to name this one VWT. So make sure you match up the corresponding vertices if you're writing your congruence statements. Then in example 2. Example 2 says, suppose it is given that segment CF bisects angle ACE and angle BFD. Write a flow proof to show that triangle CBF is congruent to triangle CDF. So we've had a 2-column proof that we've already looked at. What a flow proof is kind of like a flow chart, where you put information in boxes and then you draw arrows going to the next information that they link to. So let's just look at what we know in this problem. If we knew CF is bisecting ACE and BFD, so CF here is bisecting angle ACE, and then angle BFD. So that tells me these 2 little angles down here are equal, and these 2 up here are equal. So what else do we know? Well, we know angle 1 is going to be equal to angle 4. How do I know that angle 1 is equal to angle 4? I know that based on some of the other information along these bisectors. If I knew this angle down here was equal to this one up here equal to this one, I would also know 2 is equal to 3 or congruent to 3. So 1 has to be congruent to 4. Just part of the info. But let's start over here. They gave us CF bisecting ACE and BFD. So we write the info in a box. Reason goes next to the box, which was given. What that leads me to being able to say is that angle ACF, so ACF there, is congruent to angle ECF. And that's from that definition of an angle bisector. Then, I also know angle 1 and angle 2 are supplementary. They're a linear pair. Angle 3 and 4 here are supplementary. So that's the definition of supplementary angles, or the linear pair theorem. Either one says that those 2 angles are supplementary. So if I knew 1 is congruent to 4, and I know that 1 and 2 are supplementary and 3 and 4 are supplementary, I can use the congruent supplement theorem to say that 2 is congruent to 3. Because if 1 and 4 are the same, and then if 1 is supplementary to 2, 3 is supplementary to 4, using the congruent supplement theorem, that tells me angle 2 is congruent to angle 3. What I also know in this problem is CF, that the 2 triangles that I'm trying to prove congruent, it's congruent to itself. So segment CF is congruent to segment CF by the reflexive property. That one doesn't have any arrows leading to it because that's just an extra observation made off the image. But now I can take my info that I have. I know CF is congruent to itself, ACF and ECF are congruent, and angle 2 and angle 3 are congruent. So now I can say triangle CBF, this one here, and triangle CDF are congruent by angle, angle, side. So just another way to write out a proof. This is a flow proof pattern, gives you a little more fluidity, and then you draw arrows connecting your ideas. So you're not stuck in the 2 columns setup. Then we get into our final 2 examples, examples 3 and 4, based on these word scenarios. Anytime we're dealing with triangles and word scenarios, I'd recommend taking the time to either highlight the given information or draw a picture as you go if one's not provided. So this word scenario says you and a friend are trying to find a flag hidden in the woods. Your friend is standing 75 feet away from you. When facing each other, the angle from you to the flag is 72 degrees, and the angle from your friend to the flag is 53. Is there enough info to locate the flag? So again, drawing a picture will help us start to understand the scenario. So I would just start with a dot for you and a dot for friend, connect them, and we know that distance is 75 feet. Now, if we're facing each other, I know the angle from myself to the flag is 72 degrees, and the friend of the flag is 53. So that means my flag would be somewhere out in this location. So is there enough info to find this flag? Yes, there is. Because if we were given the 75 feet here, and then the 53 and 72 degrees, we have an angle, an included side, and an angle. Any triangle with these given measures of 72 degrees, 75 feet, and 53 degrees are all congruent to each other. So based on what we know, we could calculate either of these distances to find the flag. So we could, in any triangle scenario here, even if this moved from a forest to a grassy backyard to wherever it may be, if we have these 3 measurements, all those triangles are congruent. So that means we could always calculate the location of the flag. We don't actually need to solve it, but yes, there's enough information to do so. And then in example 4, theater example. You are working 2 different spotlights for a play. 2 actors are standing apart from each other on the ends of the stage. Spotlights are located and pointed as shown in the diagram I gave you. Can one of the actors move without requiring the spotlight to move and without changing the distance between the other actor? So what we know according to our diagram is we have our 2 actors on a stage with 20 feet in between them. Then we had the right angle coming out here, and here we have where the spotlight is. So our location here of the spotlight, and this 40-degree angle aiming one here and one here. So that's our diagram of info. So we have a 90-degree angle, a 40-degree angle, and a 20-foot side. So I can look at this going angle, angle, side. So all the triangles that are 40-degree, 90-degree, and then 20 feet need to be the same exact size and distances along the sides. So if any of these things changed, so if this actor moved 1 foot over here, that means we would have to change the angle of the lights or the distance from the actors. So what it's asking is, can one of the actors move without requiring the spotlight to move and without changing the distance between the actors? No, because if this actor would move here, that would change the distance, even if that angle stayed the same. Or if he would move out here, that would change the distance and the angle of the spotlight. So because we have angle, side congruence theorem, if we would change one part of that, so move an actor in any direction, that's going to affect the rest of the setup. But the main idea for this lesson goes back up to postulate 21, angle, side, angle, and theorem 4.6, angle, side.